So what I want to talk about is a view of the 10 to 30-year future in fundamental physics. And as you all know, this is an especially appropriate time to be thinking about this, since we've had the dramatic discovery of the Higgs, that in many ways is a logical completion of much of the structure of 20th century fundamental physics. I'll also have, this is, yeah, so, so we really are at a very important crossroads in the development of our field, and it's important to think carefully about what we're going to do next. So that's what I'm going to talk about. And I think I want to start by very quickly summarizing what we learned in the 20th century. In a sense, the next few transparencies are really the most important things that we learned about, the most important fundamental things we learned about physics in the 20th century. We start with a very basic seeming observation, almost trivial observation, that we live in a big universe. There's a big space-time. And well, that's one thing that we learned, is that there is such a thing as space-time, so there's relativity. But the universe is big. There's this nice big flat space-time. And there are, in this space-time, there are light elementary particles that operate according to quantum mechanical laws. So, given the fact that the universe is big, given the existence of a big space-time, and given relativity in quantum mechanics, the really signature accomplishment of 20th century physics was this slogan that I've said many times before, and actually I think it goes back to Steve Weinberg, who's really the person who articulates this point of view most clearly. What we really learned is that these basic principles of relativity and quantum mechanics, taken together, almost completely dictate what the structure of the laws of nature can look like. This is an extraordinary fact. It didn't have to be true. If we only had quantum mechanics, it's definitely not true. We can write down zillions of different possible quantum mechanical theories, take a random Schrodinger equation, random potential, a continuous infinity of choices and freedom we have in what the world can look like. If we take only relativity, similarly, tremendously, relatively unconstrained. But relativity and quantum mechanics together almost completely dictate what the universe can look like at long enough distances. And we're used to talking about this when we teach courses in the great tension in putting special relativity and quantum mechanics together that forces this very rigid structure of quantum field theory on us. And if this was another talk, or if I had longer, I would actually spend some time explaining the statement from a more fundamental starting point. Really just beginning with those rules of relativity and quantum mechanics and building the only consistent possible theories we can have. But anyway, it's true. And the more precise statement is the following. Oops. Oh, okay, that's fine. Well, so let me say, yeah, I had taken some of these pictures out, but anyway, it's fine. So the more precise statement is the following: that since the elementary particles are light, it makes sense to imagine what the physics can first of all look like at energies much, much larger than their mass. Okay? So for the energies much larger than the mass of the particle, we should be able to ignore the masses of the particle in the first approximation. And so we'd like to talk about the consistent possibilities for interacting in massless particles. That's the question that has a very rigid answer. Okay? If you just try to write down the only consistent possible interacting theories for massless particles, you find that it's almost impossible to do so. Okay? And that in the end, the only consistent theories for interacting massless particles you can have, the only spins they can have, are particles of spin 0, 1/2, 1, 3/2, and 2. Okay? And furthermore, you discover that that spin 2 guy is unique. It's GR. Okay? The spin 1 guys, you can have a bunch of them, but they have to have a very, very rigid constrained structure, Yang-Mills theory. Except we never talk about Lagrangian or gauge symmetries or path integrals or all that stuff is great. All that stuff is even correct from some, is of course correct from some points of view, but it's not necessary to arrive at this very deep conclusion. These conclusions follow very directly from just trying to write down consistent interactions for these particles. Anyway, so, and before July 4th, 2012, we were in the interesting situation that, of course, we'd seen particles of all these spins in nature before, okay? Before this argument was really deeply appreciated. But the particles that we'd seen had spin 1/2, 1, and 2. So, so we're in a peculiar situation that nature can apparently do more things than it's chosen to do, right? And that's what's so important about the discovery of the Higgs. The discovery of the Higgs is the first time we added to this table. Okay? It's the first new elementary spin 0 particle that we've ever seen. We've never seen it, anything like it anywhere before, anywhere else in physics. It's exquisitely simple on the one hand. It's extremely mysterious. That simplicity is extremely mysterious on the other. But anyway, it is an example of something nature could do that it did do. It's something it could do compatible with these basic principles that now we did see it do. And now actually the only thing that's left that we haven't seen it do is the spin 3/2 guy, right? And the spin 3/2 guy can only exist if nature is supersymmetric. So that's the real reason for excitement about supersymmetry. The deepest reason. Of course, it might solve the hierarchy problem. We might see it at accelerators. We might still see it at the LHC. We might see it at the SPPC and so on. But the deepest reason for the excitement about supersymmetry is that supersymmetry is, in a sense, it's the answer to the question, what's the last thing nature can do compatible with the general properties of relativity and quantum mechanics that we haven't yet seen it do? It's the last thing it can do that we haven't seen it do. Okay, so now that entire extremely rigid story is for massless particles, and therefore it must hold, no matter what's going on, it must hold at sufficiently high energies when you can ignore the masses of the particles. Okay. As you all know, the entire story of the Higgs really has to do with smoothly interpolating between massive and massless. Okay. So we don't have massless particles in nature. We have particles that have a mass, and particles with spin that have a mass have a peculiarity, that there's a discontinuous change in the number of degrees of freedom between massless and massive particles. Right? So even for spin 1/2 particles, a massless particle, there's no reason it needs to have the left and right components should be treated the same. There's no theoretical reason, of course. It isn't. Parity is violated. And yet, when you make them massive, we have to have 2 degrees of freedom. So you have to jump from 1 to 2 degrees of freedom when you go from massless to massive. Even more dramatically, when you go for a massive spin 1 particle, you've got to jump from 2 to 3 degrees of freedom. Okay. And so there's a discontinuous change in the number of degrees of freedom. And therefore, because of that, it's not just a simple matter of kinematics to ignore the mass as you go to very high energies. You have to understand what the extra degrees of freedom are doing. The question becomes, how do we take the massive particles that we see at very low energies and reassemble them into these consistent building blocks that we're allowed to have at very high energies compatible with these principles of relativity and quantum mechanics? Okay? And the Higgs is the answer to that question. And it's something that's, it's not the historical path for discovering it. Historically, people imagine symmetry breaking and drawing Mexican hat potentials and things like that. But in a sense, that's not the deepest aspect of the Higgs. The deepest aspect of the Higgs is that it allows us to take the world of massive particles at long distances and continuously interpolate it to massless particles at very short distances and very high energies. And of course, at very high energies, all these degrees of freedom, the longitudinal components of the W's and the Z's and the Higgs, reassemble into precisely those interactions that we're allowed to have compatible with these general principles. So, with the discovery of the Higgs, really something has changed. And I think this is really important to emphasize in talking about what the future of our field is going to be, because independent of budgets and governments and politics, independent of all that, forget about all that for a second. Something has actually changed with physics, right? I mean, the state of fundamental physics is different today than it was 50 years ago. And the basic questions that we have today even have a different character than they had 50 years ago. It's not just, what's going on now is not just the analytic continuation of what happened 10 years ago or 20 years ago. Because with the discovery of the Higgs, for the first time in our history, really ever, we finally have a self-consistent theory that works. It describes things that we see in experiments. And at the same time, it doesn't predict its own demise as you go to very high energies. It's self-consistently possible to extrapolate it to exponentially high energies than we're at. We've never been in that position before, right? We've always either had a puzzling phenomenon we didn't understand, or the theory that we had predicted its own breakdown, just within a factor of few higher energies than we went. But that's different now. Now we have a complete framework, and in a sense, the story of the Higgs is completing this understanding of 20th century physics. It's completing this whole structure. Relativity and quantum mechanics completely force what interacting massless particles can look like. All you get to do is choose a menu of those particles and their spins and the interaction strength that they can have. That's it. That's all the freedom you have. And the story of the Higgs is fills in the last gap about how to convert massless things at very high energies into massive things at very low energies. Okay. So with that gap, we can now self-consistently go into the regime where everything looks massless, and where we see what the basic laws are most nakedly. Okay. So that's one big piece of 20th century physics, which has been completely put into place. I want to make a few comments about inflationary gravity waves, because this is obviously very, very big news. And I should say that, at least certainly locally around Princeton, I'm surrounded by people who probably more than anywhere on the planet are very skeptical about the BICEP result. Some of them started off skeptical from the very beginning. Some of them started very enthusiastic and are now very, very skeptical. So this is either the greatest discovery in cosmology in 50 years or it's dust. And we're going to have to wait and see. But nonetheless, let's proceed by assuming that it's actually real. I think there is a reasonable chance that it will, R won't be 0.2, but I think there's a very reasonable chance it will be 0.1, and something will survive from this story. But I want to mention it because I cannot resist talking about it. A, because it's huge news, and B, because the symmetry with what happened with electroweak symmetry breaking is perfect. Okay? There's a perfect analogy between the story of inflation and the story of electroweak symmetry breaking, and I cannot resist talking about it a little bit. Okay. So anyway, obviously, it's deliriously exciting if it holds up. And something that I think is worth emphasizing is that this is not at all crazy. Somehow, it's gotten out there that this idea that R large at this level of 0.1 or something is something sort of crazy. Not only is it not crazy, it's the simplest thing you would expect. And there's a reason why the very, very first people who built inflation models, by the way, it's always happened that fundamental physics in our understanding of elementary particle physics is the cart that drags, is a horse that drags all the other carts behind it. This was also true in the 1960s and 70s. In the development of the standard model, before we had a good picture for what was going on with the strong interactions, it was impossible to even think about early universe cosmology because everything broke down the second temperatures became comparable to the hadronic scale. So we needed a good understanding of what was going on with elementary particles in order to even be able to contemplate what early universe cosmology looked like. And then all the ideas, theoretical ideas that were developed in order to understand the nature of elementary particle physics, in particular the whole idea of Higgs fields that can fill the universe and have expectation values and as dynamical objects. This is something that was very, very much in the air. It played a crucial role in the Standard Model. And one of the motivations for the early inflationary pioneers was to think about the Higgses for grand unified theories. And the Higgs particles for grand unified theories could have the sorts of potentials that would lead to inflation. So right from day one, they were thinking about energy scales as high as the gut scale. And those simplest models, indeed, would give you large gravity-based things. So it's actually totally totally reasonable, at least from my point of view. And it would be amusing if this result holds up. This, if R is around 0.1 or 0.12, that's completely compatible with a very simple m squared phi squared potential. And so this would be the decade of discovering weakly coupled scalar fields. Okay, the decade of m squared phi squared. We'd have m squared Higgs dagger Higgs, and then a few years later we'd have m squared phi squared. Okay, I don't want to talk about that. But let me just say briefly what this analogy is between the physics of electroweak symmetry breaking and of inflation. Because, in fact, what we see from inflation is in a sense, the early days of the physics of electroweak symmetry breaking. What we have direct evidence for, if you believe in what we have direct evidence for, is that the universe had this inflationary phase where it was expanding with the inflationary rate slowly slowing down. And if you want to build models for where that comes from, you would say, oh, you put in scalar fields with funny looking potentials and so on. But in fact, whether you like it or not, whether it comes from those models or not, if this background exists, all you need to do is believe that this background exists for some reason. Okay? This background with the inflating cosmology. And then immediately there is that scalar field degree of freedom. The reason is that there is a clock. Okay? Inflation, it's not time translational invariant. It starts and then it ends. And there's a clock that tells you how far along you are in that process. That clock is a physical, dynamical degree of freedom. Okay? And it's a direct consequence of the breaking of time translation symmetry. Okay? So we have a background, we have a phenomenon, the thing that exists, this inflationary background. And associated with that, there's a Goldstone mode, which is the clock, which in most inflationary models would be called the inflaton. But it's really some of the more general thing. It's the degree of freedom that must be there because of the symmetry breaking pattern. That's almost identical to the story of the longitudinal components of the W and the Z, right? The second you say that the W and Z are massive, whether you like it or not, there's an extra scalar degrees of freedom there, the longitudinal modes, right? Now, in the case of W's and Z's, we learned a little bit more. If you just have massive W's and Z's, there's no reason why the W and Z masses should be anywhere near each other, and yet they're pretty close to each other, right? Today we know that that's the case because the physics has an extra global symmetry, the custodial symmetry. There's an analog of that global symmetry for inflation as well. So the analog of the W and the Z having comparable masses is whether the fluctuations around this background have the same speed of sound, right? Whether the clock speed of sound is the same as the speed of gravity, or the speed of light. And again, a priori, there's no reason they have to be the same. We've broken Lorentz invariance after all in this background. So a priori, they don't have to be the same. If the bicep results hold up, the speed of sound must be comparable to 1. It can't be much smaller than 1. That would greatly enhance the scalar to tensor power for simple reasons. So we're getting evidence that in fact there is an enhanced global symmetry that makes the speed of the clock comparable to the speed of comparable to 1, and that enhanced symmetry is an approximate de Sitter symmetry. Okay? So the analog of custodial SC2 is an approximate de Sitter symmetry. Now here, people wanted to find UV origins for the longitudinal modes, and the simplest idea is that those scalar degrees of freedom are, in fact, derived from scalars in the underlying theory. And that's what we get from Higgs models, right? The analog of that in the context of inflation are every model of inflation that anyone writes down, right? You have some scalar fields, and indeed, the clock is a scalar field. That means that the clock during inflation survives in our universe today as some particle that could in principle be produced with very, very high energy collisions, right? But we also know from the analog in electroweak symmetry breaking that it's possible to imagine other kinds of physics where those scalar degrees of freedom have nothing to do, the longitudinal modes have nothing to do with scalars fundamentally in the underlying theory. And that's, I think, one of the interesting frontiers in theoretically thinking about inflation, is to find the analog of that for inflation. This would be some physics driving inflation where there's nothing recognizably like an elementary scalar field in it. But we know, because everything follows from general symmetry grounds, that it doesn't matter. As long as you get the exponentially expanding background, you're done. All the other predictions are going to follow that we've seen so far, because they're just a consequence of asymmetries. And I think this is a really interesting avenue to think about and explore more. All right. So, now, in fact, if all of this stuff holds up, so inflation is like just seeing massive W's and Z's. But in the context of electroweak symmetry breaking, there's a whole world that came after that, right? And you want to now start seeing the sort of dynamics of what's going on. And I think in the far future, the analog of that in cosmology is going to be cosmological collider physics. Okay? So there's a statement that we all make when we talk to journalists when it comes to inflation, is that, well, we have access to these very high energy scales. The universe is like an accelerator probing very, very high energy scales, right? And this is something we tell journalists. But what I'm saying is it's something that we actually have to do. And doing it is going to involve a number of really interesting new conceptual things. Just to give you the analogy, when we do collider physics, we start off life with stable particles, like quarks and leptons, right? And first you have to see that they're stable. That's great. After you see that, you collide them into each other. Fortunately, at short distances, the collisions are weakly interacting. Perhaps we make some new particles, and they decay back, ultimately, to the stable particles. And in fact, in the real world, even the quarks hadronize. They eventually become strongly interacting at very large distances, and we see jets. And from the correlations between all those jets that came out, we try to infer something about the new particles that we produced. Okay. The analog of that in inflation, the analog of seeing these particles is just seeing the density perturbations, the Gaussian density perturbations. That's just like seeing the freely propagating particles. But the early inflationary phase is giving us this thermal soup where these particles are colliding with each other. And if we have particles that have mass not too far from Hubble during inflation, we can actually produce them. We can produce them and they'll decay back to the inflaton. And just like here, even this part of the story, the jets has an analog. The short distance collisions here are very weakly coupled. It's down by Hubble over M Planck, let's say, 10 to the minus 6 is the coupling, really weakly coupled. But eventually, at long enough distances, they do become strongly interacting and they turn into galaxies, right? So the analog of jets in cosmology is galaxies. And indeed, by looking at the correlations, and in fact, the non-Gaussian correlations that we get, using all the possible information down to nonlinear scales, we should be able to reconstruct what was going on here and start learning how to do collider physics. How, from the information of the non-Gaussianities in the sky, can we see that there's a particle there that weighs 2 times 10 to the 14 GeV of spin 2? Okay, all that information is there, and it's really interesting, even theoretically, to start thinking about how to extract it. And of course, it's an experimental program on the 2-3 decade time scale. So many people have talked about non-Gaussianities in inflation for the last 10 years. But this specific question about what fingerprint you look for in the sky for actually producing the new particles is something that we can think about and work on. It's something that I'm working on now. I'm starting to think about with very preliminary thoughts with one more this in. Okay, sorry. All right, so that's the so that's just sort of quickly saying that I think the Higgs and inflation together are conceptually very closely related to each other last chapters of 20th century physics. And they're very important, and thinking about them more is going to be very, very important. but they're closely tied to these old ideas from the last century. What I want to spend my last few minutes talking about is instead what the zeroth order big questions are for the 21st century, and the critical role, absolutely critical role, big circular colliders are going to play in entropy. See, at least now there's many questions that we could be talking about, but I just want to focus on the few which are, and really two of them, which are, in a sense, at least in my view, the most big picture overarching questions. And it really goes back to the beginning of the 20th century. We started by saying that once you take for granted that you have a big universe with space-time and quantum mechanics, then the machine runs and you largely predict what the world looks like at long distances. The amazing thing is that this starting point from a number of perspectives seems very strange. So once you accept the starting point, everything is very constrained and follows. But where the starting point came from to begin with is now the biggest question on the table, especially because it's so mysterious, in fact. So how and why did it come to be that we have quantum mechanical laws in a big space-time? And in fact, there are two interrelated aspects of this problem. One is that these very ideas, the very notion of space-time and quantum mechanics are likely not final. This is almost certainly true for space-time. There's many reasons to suspect that space-time can't exist fundamentally. It has to emerge from something more primitive. And it's even possible that for subtle cosmological questions, not for anything in anyone's lab, for any practical issue, but for subtle cosmological questions, quantum mechanics is incomplete, and it needs to be extended into a broader structure. So again, we have to see quantum mechanics emerge from some more primitive principles. So these two big conceptual underpinnings of 20th century physics are both things that aren't actually aren't likely to survive. And secondly, what got us going to begin with, which is that the world is big, we have no good explanation for it. I think this should be the sort of thing that wakes you up at night, right? It's maybe the most basic fact about our world is that it's big, even though it's made out of small things, and even though the laws have quantum mechanical fluctuations that are more and more violent at shorter and shorter distances. Enormously violent quantum mechanical fluctuations that would seem to want to destroy order at large scales, and yet here we are living in a nice, big, comfortable universe. So so the question of why the universe is big to begin with is a cosmological constant problem. The reason why this big universe has big things in it is the same as the weakness of gravity. That's the hierarchy problem. And those are, I think, the questions that are at stake. See, in my view, these central questions are not about details. Much of the last 40, 50 years was about very important details. You know, what precisely is the menu of particles that we have? To really understand the quantum field theory works, so we don't need to abandon it every time a new experimental phenomenon happens, right? That was very, very important. But when the story of 20th century physics is written, it will say, in 100 years, they won't make such a humongous deal about the standard model. They'll make a humongous deal about relativity and quantum mechanics, and then they'll say, then people went off and they explored and they showed that all this stuff works. It just works, right? But it's not as big a deal as relativity and quantum mechanics. What I think is so fascinating about where we are today is that we're in another situation that doesn't come along all the time. We're in another situation where foundational things are at stake. So there are these deep structural questions about the origin of space-time and the macroscopic universe. And the light-Higgs discovery is an absolutely crucial part of this story. Okay? So this I cannot emphasize enough. Some people would have been much happier if we hadn't discovered just the Higgs. We discovered something complicated like Technicolor. Okay? These people would have been happy because they would get to repeat the 1960s all over again, right? They would go, there would be resonances, we would measure all of them, we'd have to see what's going on. It's exciting, it's very interesting physics. It continues to be very interesting physics. QCD continues to be very interesting physics today. Okay? I think if that had happened, we would not be learning something qualitatively new about the world. In fact, that kind of physics we've seen in QCD, we've seen all over the place in condensed matter physics. Okay? Generating large hierarchies of scales through strong interactions is the only way we've seen in nature before this thing happen. Right? The fact that instead, in the vacuum of our universe, we see something which is the polar opposite of that. One weakly coupled scalar field, exquisitely unnatural, so far at least. Okay? Not seeing any new physics, we have no idea where to get this from. Any place that we've seen elsewhere in nature, either in the laboratory or in the theoretical laboratory, where we manage to get light scalar fields, they have to come accompanied with lots of other new physics to go along with them, because that's the famous naturalness problem. And it's not a problem that's just invented out of the head of theorists randomly. This idea of naturalness explains why it is in condensed matter systems. When you pick a random condensed matter system, you don't see it have light scalar fields in it. You don't, because it takes fine-tuning in order to get light scalar fields. So it's astonishing that the physics of our vacuum is making a choice that looks like that. It's absolutely astonishing. Okay? We don't care about making new particles for the sake of making new particles. Okay? Particle physics was the same as fundamental physics in the last 50 years, because discovering new particles was the best tool for discovering new principles and new laws. What we really care about are new principles and new laws, not new particles for the heck of it. And that's what's amazing. If we discovered something complicated like Technicolor, we would not be really discovering new principles or new laws. We'd be learning another detailed aspect, just like everything that came before it. Seeing the light Higgs and nothing else is giving us a profound opportunity, because we've never seen something like it before. Okay? And in fact, we've never seen an elementary spin zero particle before without substructure. Obvious substructure on the scale of its mass. So that's the most important thing that we need to do with the discovery of the Higgs. We have to see if it has substructure. We have to see if it looks point-like. Okay? The more and more point-like it looks, the more and more shocking it is. The more and more, the less and less it is like anything we've seen before. And anyway, so this is not just hype. It's not just something we tell journalists, you know, but secretly we're like, oh, it's kind of boring. You know, it's exactly the other way around, at least as far as I'm concerned. It's the strangest and most striking thing that we could have seen so far from colliders. To see the Higgs and nothing else so far is, I think, had you told me or any of my friends in 1995 that that's what was going to happen, we would have been stunned. Okay? The very simplicity is very striking, it's very suggestive, and so we have to explore the Higgs and we have to explore the quantum fluctuations of the vacuum to as high energies, short distances as we can in order to understand where this amazing physics is coming from. All right, so I've basically used up all my time, so I'm not going to be able to go through the arguments for the detailed arguments for why this is the experimental future. But I think it's clear that the experimental future is our great big circular colliders. First in the form of the Higgs factory, and then ultimately as a 100 TeV or 100 TeV scale, maybe less, but in that neighborhood, proton-proton. And I've said this many times before, probably many of you have heard me say it, but even before talking about detailed reasons why we should go do this, this is just the absolute obvious future. These big machines, big physics ideas are what have kept our field going for centuries. And you know, it is important to remember that fundamental physics has survived many, many hardships in the development of humanity over the last 4 centuries. Okay? It hasn't all been roses the whole time. There's been wars, there's been famines, there's been every possible disaster. And yet, this subject keeps going. Why? Because it's what humanity does. It's one of the things that makes us human. And so when we think about, is it hard? Can we afford it? You know, we have to think, if we don't do it, then this will be the time. Of all the times in the last 400 years when this could have ended. This will be the time that it ends, right? And I don't know about you, but I have a very powerful sense of sort of moral intellectual responsibility. We've been handed this subject by Galileo and Kepler and Newton and Einstein and all these guys, and we have to push it forward, right? If it fails on our watch, it'll be on our heads. And I think it's too terrible a thought to contemplate. So it's the absolute obvious future, but you know, a little more detail, how precisely to proceed, precise timelines, precisely what you do and so on, of course will depend on the first LHC 13 results. But I think in every scenario I can imagine, we're going to need these machines. And this is not just the first statement that we should just keep going no matter what. This is reflecting a new bit of physics that we've seen the Higgs and nothing else, right? If it was the picture of new physics that many people contemplated in the mid-90s, it's not obvious that the next step would be to go eventually to a big circular proton-proton collider. Because in that picture of the world in the mid-90s, the gluinos weighed 300 GeV, would be making millions of them, 10 million of them at the LHC. All the superparticles will be in our lap already, say, if it was supersymmetric. And then maybe you need a linear collider to do very precision studies of the electroweak part of the spectrum. That was the vision. That was the vision of 2 decades ago. And that vision does not seem relevant today, right? Not because there's anything wrong with it, but just that's not the choice nature has made, okay? We've seen the Higgs and nothing else yet. And that means that it's A, much stranger than we imagined. Many of our theoretical prejudices are being challenged by this. We have to study the Higgs in tremendous detail, obviously. But even if there is new physics, and even if we start making it the LHC, the fact that we haven't made it so far means that we're not going to be making millions of these particles, right? So no matter what, in order to get access to whatever is going on, even if we make some of it at the LHC, we're eventually going to have to go to much higher energy. So both the Higgs factory as well as the proton-proton collider option are necessary. And since I'm out of time, I'll just list at least what I think the sort of what the physics argument for these accelerators is, or the sort of 3 big legs that it rests on. Well, as you know, there's a lot of work going on here to prepare sort of pre-conceptual design report for the CEPC SPPC project, and there's a lot of very interesting work going on. We're going to be talking about much of it in the coming months. But at least in my own thinking, I think the argument for pursuing these projects rests on 3 legs. One is really a direct continuation of the discovery of the Higgs, which is that we obsessed for a long time with what breaks electroweak symmetry. So we'd like to know the answer to the question, how is electroweak symmetry restored? Okay? We know what breaks it now. But it's like seeing the Web for a long, long time, is all we saw. Now we've seen the first tiny excitations around the bottom of potential. But we'd like to know the answer to the question. Just like historically, understanding QCD let people extrapolate cosmology to much higher energies, we'd like to know what happens in the early universe as we go to much, much higher temperatures. And we'd like to know, what does the phase transition look like? Is it first order? Is it second order? We'd like to have experimental handle on these questions. Of course, if you believe in the standard model, you know what happens, but we'd like to experimentally probe this. This has nothing to do with naturalness, it has nothing to do with fine-tuning. It's really directly, we've seen an electroweak symmetry breaking, now we'd like to see how it's restored. And what's really nice about this argument, so if you want to probe the physics of the unbroken SU2 cross U1, you precisely need both of these things. You precisely need to have a Higgs factory that gets you percent to per mil level precision on Higgs couplings, and a 50, 70, 100 TeV proton-proton collider. Okay? And when people ask, well, we don't know, you don't know what the next scale is, you don't know whether there's any new particles there, how do you know you need 1% accuracy for the Higgs? How do you need 10 to the minus 3? Why not 10 to the minus 4? Why not 10 to the minus 7? Or how do you need to go to 100 TeV? Why not 1,000 TeV? Right? You don't know what you're gunning for. There's no milestones. Well, for this question of probing the electroweak phase transition, there are milestones, okay? if the particles are going to affect the structure of the electron beam phase transition, they cannot weigh 10 TeV. They can't even weigh 1 TeV. Okay? They have to be a few hundred GeV at most, and they have to be relatively strongly interactive. Right? This is something many of you know, but we could be finished with everything we know about the Higgs from the LHC. We could know the Higgs couplings at 10%, and it could still be totally consistent with the first order phase transition. Okay? That's a very unsatisfactory state of affairs. So we'd like to know experimentally what that phase transition looks like. And in order to do that, any new physics that does affect the phase transition has got to be light enough and strongly coupled enough that it must give you deviations in precision Higgs couplings, and you must be able to produce the new particles in the high energy collider. Anyway, so that's one argument. So we can talk about this later, anyone who's interested. Secondly is the fate of naturalness. And this is something that's been talked about at length, so I won't go on and on about it here. But if we don't see anything but the Higgs at the LHC, we'll have evidence for fine-tuning in nature at the 1% level. And 1% is just not so dramatic that it's a big enough deal to completely change your philosophy about what the laws of nature should look like. We've seen many other 1% accidents in physics before, which have not had that impact on the way we think. And technically the reason for it is that a 1% level accident is compatible with what you might call a look elsewhere effect. Okay? You say, is it reasonable the Higgs mass squared parameter might be tuned to 1%? I don't know, we have 30 parameters in the standard model. 30 is comparable to 100, right? So maybe one of them looks a little funny. We're all familiar with something that looks a little funny when you've done many measurements, okay? So, and there are many other accidents in nuclear physics and other parts of physics that are of this level that have not been, that haven't been used to justify completely changing our philosophy about what the laws of nature look like. If we see the Higgs and nothing else, then either the particles really are there, we're a little unlucky, we missed them, it's just percent level tuning. In that case, the new particles must give you effects that can be seen in precision Higgs deviations at the Higgs factory, must. This is actually a big deal, because you can't even hide them using any of the loopholes that model builders like talking about. For instance, when I said that the LHC says that if we see the Higgs and nothing else, we'll be tuned at 1% for the LHC, that's assuming that the partners of the top are colored. If they're not colored, it could be totally natural at the LHC, and we will never know it just from the LHC. However, colored, uncolored, whatever the heck they are, if there is something that couples to the Higgs that makes it natural, it must give you at least percent level deviations in Higgs couplings. And it cannot be hidden from the CEPC. And of course, you have to be able to produce them, the particles at the SPPC. So this is actually, there's a better version of this plot. This is the stop reach at 100 TeV colliders. The better version goes up to around 9.5 TeV now. And these particles, whatever they are, colored particles, colored, uncolored, whatever they are, if they talk to the Higgs, they have to give you this for Higgs interaction, which turns into, when you put two of the Higgses to their bed, turns into deviation in a universal Higgs, deviation in Higgs couplings. And this is something that, again, you must see at the Higgs factory, you must be able to make the particles. And I won't go through these plots in detail, but anyway. So, and there's a variety of other things. You know, if we do see the new physics at the LHC, just what we said already, we're not going to make so many of the particles. You know, if it's gluinos at 2 TeV, we'll make 10,000 of them. Wonderful. We're not going to make millions of them, right? To make millions of them, to really study what's going on, we're going to have to go to a much higher energies. And it's also unlikely that we're going to see the whole story at the LHC, even if we start making natural new particles. So, all right. Finally, but I won't go talk about this because I think Leontel will talk about in his talk, but the third leg is to get a very robust probe of weakly interacting particles in the 1, 2, 3 TeV region. Okay? If you want to, it's very reasonable to have weakly interacting particles in the 1, 2, 3 TeV region. If we just have particles annihilating through the ordinary standard model gauge interactions, that's the kind of mass they would need to be thermal relics. The LHC was never the machine to probe particles, weakly interacting particles at that scale. If you want to get to weakly interacting particles in the 1, 2, 3 TeV regime, you need to eventually go to very high energy proton machines. All right. So anyway, those are the three big arguments. The physics of electroweak symmetry restoration is just a direct continuation of the Higgs discovery. And the ultimate fate of naturalness. Both of these things are in one way or another conceptually about the question of, is there a substructure to the Higgs? And is the Higgs point-like or not? Every scale that we've seen in nature before has been very composite. Okay? So the Higgs is looking pretty point-like so far, and it's so surprising that we need to look at it with as powerful a microscope that we can and see if it continues looking point-like down to very short scales. Either it does or it doesn't, but either outcome is a humongous deal because there is not one or, there's no nightmare picture. We're so confused about what's going on that either solution is going to throw us down one road or another for what it means more deeply for fundamental physics. Okay, so, but I also return to this statement that these machines are the obvious future of our field. And ask not what you can do for circular colliders. Ask not what big circular colliders can do for you. Ask what you can do for big circular colliders. In the famous words of all right, so let me end by saying that, really repeating what I said in the beginning, but at least in my own view, the scientific questions that are at stake in our field today are the most difficult and profound ones that we've faced since the birth of relativity and quantum mechanics. And because the problems are so big, the scale of our vision and our ambition, on both theoretical and experimental points of view, has got to live up and commensurate with the singular tasks at hand. So, there's an enormous amount of work to do. I think very exciting work to do, and I look forward to seeing the talks in the rest of this meeting. Thank you.
So, in the industry, then we are always moving forward step by step. But here down, you stress on some fundamental theory. So, what do you mean the fundamental? So, see how far we are from the real fundamental theory.
Well, I think at any given point, which is something you know very well, but I think we all know well, but it's worth emphasizing. At any given point in the development of physics, there are some very big scale questions which are always there. They were there 2,000 years ago. The ancients could have thought 2,000 years ago, what is space, what is time, where does everything come from, right? The art of doing real science rather than just, being in college and smoking, right? And the art of doing real science is to figure out what is the next question, just as you're saying. What is the, not what's the deepest question, but what is the next question? The next question that's hard enough to be worth spending time on, but easy enough that you have a hope of making some progress on it, right? And so it's a really good idea to think about what the next question is. What I find amazing, and again, I stress that, it sounds grandiose, but it sounds grandiose because it's the way, what I really believe. I'm not exaggerating the claim, is that 50 years ago, the next question did not involve thinking about these deep questions about space, time, and all these things. Absolutely not. It would have been stupid to spend time on this, okay? But today, the next question is that. And that's what I find amazing. Okay? Today, it's true that the very next questions, and it's a mark on the one hand of how much we've accomplished, right? We understand an enormous amount about the way nature works. We're not in the situation that if a new particle comes out of an accelerator, that people are going to be shaking or going to be wondering, how the heck do I even start thinking about this and what's going on? Every graduate student, every undergraduate, in China, every high school student will write down a Lagrangian and immediately will know what to do, right? That's not the same as it was 50 years ago, okay? We're in a conceptually different position because we understand the world much better. And therefore, it lets us ask a different character of question. I mean, I'm stressing this point because it's relevant to the question of, is it worth just studying the Higgs? What if we don't see any other particles other than the Higgs? Isn't it a disaster? There's just the Higgs. If your view of physics was that what you care about is new particles, it is a disaster. But that's not the purpose of physics. It's not new particles for the sake of new particles. It's new particles for what it's telling us about the basic structure of laws. And the amazing thing is that where we are, as far as understanding the basic structure of laws goes today, is at a qualitatively different place than we were in previous eras. The character of question is totally different. It's one level up, and it's much closer to these very deep questions. I mean, the naturalist issue for the Higgs is right side by side with the question, where is the universe? Why is it there? Why is it big? Where did it come from? Right? It's not unconnected with that. And then, of course, there are these theoretical issues that I didn't talk about at all that we're unlikely to get direct experimental clues about, but about the ultimate origin of space-time and quantum mechanics. Those are the next questions for theorists. It's not like there's 10 other simpler questions between us and it. So I think we have to realize that. We have to appreciate that. We're in a different era. I mean, it's not just something we tell people. It's not just something for journalists. We're in a different era. And in this different era, we have to turn and think about what the questions are that are worth looking at. So yeah, so it's not. I agree. It sounds like these. Superficially, it might sound like this is just the same kind of stuff college kids would talk about what it all means, right? But that's what's remarkable is that these are now our professional questions, and it's what we have to work on as a profession.
Let me try to ask the questions on numbers. Going to one transparency issue on the circuit collider.
Yes.
You have that.
Yes.
So you pick up for the electron proton collider with energies 250 GeV. For PP is 100 GeV. So regarding to numbers, is you pick up your randomly or based on some fundamental source? What is the difference between 250 or 300?
Yeah. So I think both of those numbers there are squiggles in front of both of them. And they're but
So what range do you have?
well, I mean, I think for the Higgs factory going to for a circular Higgs factory going to much higher energies, like going to like 400 GeV, let's say, starts being very, very, very costly for the tower. At least that's the conventional wisdom. So so 250 is high enough that you have no problem making Higgses, lots and lots of Higgses, but you're not. For no reason, you're not busting your butt. You're not going to get so much more from going to higher energies, and there's no reason to bust your butt on the power play. For the proton-proton collider, I think this is one of the things that's going to be interesting as people start doing more detailed studies. What is it that you really? I mean, obviously, you want as higher energies as you can possibly get. But what is it that you can do? What is it that you can do with 50? What can you do with 100? What can you do with 150? Right? You know, I think there it's really a squiggle. There it's really a squiggle. I think and certainly in China, as everyone knows, the PP collider is something that will come after the Higgs factory, and it's something further down the line. But its possibility is a big piece of the excitement of this project, right? Is that you start with fundamental things about the Higgs, and it's the road to the future. So the main thing to be thinking about now is, the main thing to make sure not to do is to paint ourselves into a corner about very precisely what it's going to be that can't be backed out. So it's being left deliberately ambiguous.
Because of limited time, let's just move to the second talk. Let's thank Nima again.